Okay, let us discuss problem number 1.269. This is related to finding moment of centrifugal force. So 1.269, finding the moment of centrifugal force. Okay, let me first make the diagram for this problem and then we'll discuss what this problem is all about. So I have an axis. So this is the axis of rotation, and Irodov called this as O dash and O. And there is a point in the middle, this point they call C, and there is a rod that is attached at angle theta. And this rod is called AB. Now let me read the question. A midpoint of a thin uniform rod AB of mass m, length L, is rigidly fixed to a rotation axis O dash. So this is the rotation axis, rigidly fixed at midpoint. The rod is set into rotation with constant angular velocity omega. So rod moves with constant angular velocity omega. Find the resultant moment of centrifugal force. So this rod is moving something like this. So you see each point of rod is moving in a circular path. So this is moving in this circle, upper point is moving in this circle, this is moving in this circle, this point is not moving at all. Now this is moving in this circle. So each point, so if you consider this point is moving in this circle. So each point of the rod is moving in a circle. So I can say each point of rod is moving in a circle. What we have to find the moment of centrifugal forces. So we have to find moment of centrifugal forces. So let us say at a distance x, consider a small part of a sphere, this rod, that is dx. And let us say lambda is mass per unit length. So lambda I can define mass per unit length is m by L. So mass of dx, that is dm, will be lambda into dx. Now this is the mass of this small part. So this is a small part of the rod. Now on this rod, this is moving in a circle of radius this. What is this radius? So this is x. This angle is theta. So this is x sine theta. So radius in which dm is moving. So this radius is x cos theta is this, x sine theta is this. So this is x sine theta. Are you getting? So what is the centrifugal force? So centrifugal force is m omega square x. And this will act in this direction. So centrifugal force I can apply in this direction. So this is m omega square r, and r here is x sine theta. So now I can say centrifugal force on dm mass dm, this will be m omega square r, and m is basically dm omega square, and r we have already said this is x sine theta. So this is x sine theta. If I want, I can plot for give value for dm, that is lambda into dx. So this is lambda into dx omega square x sine theta. So this is the small mass having the centrifugal force is this. Now what is the moment of this centrifugal force about point O? So the question says find the resultant moment of centrifugal forces of inertia relative to the point C. So I have to find moment of centrifugal force about point C. So what is the perpendicular distance of this force from center? So this distance. Are you getting? So this is the distance. So you can find this distance. This is x sine theta, so this is x cos theta. So this distance is x cos theta. Are you getting or not? So this distance will be x cos theta. So moment of centrifugal force about C. This problem is easy problem. Moment of centrifugal force about C. This is going to be, this is the force lambda dx omega square x sin theta into distance. Distance is x cos theta. I have already said this distance is x cos theta. So we will have lambda omega square x square and sin theta cos theta. Theta is given to you into dx. Now I can also say this is a small moment. So moment, let us say this moment is dm. So total moment, so this is a small moment dm. I can write lambda into omega square sin theta cos theta x square dx. If I want to find total moment, I have to integrate this, and this length will go. So this side I will have negative x. So this is minus L by 2. This is plus L by 2. So the total length of the rod is L. So if I go this side, I will have minus L by 2. This side plus L by 2. Or you can do other way around. You integrate from 0 to L by 2 and then you multiply by 2. So one can also do 0 to L by 2 and then multiply by 2, because symmetry of the problem says the moment of this side will be same as moment of this side. So I can multiply by 2 and I can integrate 0 to 2. That if I take 0, I will have here, and L by 2 I will have here. So what I will have? Lambda omega square, and let us multiply sin theta cos theta into 2, that is sin 2 theta. And integration of x square is x cube by 3, and I have to integrate from 0 to L by 2. So this will be lambda is m by L. We have already said omega square sin 2 theta, and x cube is L cube by 8, and 8 into 3, that is 24. So L cube by 24, and L goes, so we will have L square only. So we will have m omega square L square sin 2 theta divided by 24. So this is the total momentum we will have. So moment of centrifugal force. This is the moment of centrifugal force we will have. I think all of you have understood this one. This is a pretty easy problem. What we have to do is, we have to first show the centrifugal force on a small mass dm, and then I have to take the moment of that small force, and then I have to integrate. So simple. Why I have to integrate? Because centrifugal moment, that is a function of x, and that's why you have to integrate. If you have here, you have different, you have here different, because x changing, moment changing, and that's why you have to integrate. I cannot simply write. Let us discuss the next problem. I think all of you have copied this one. This is an easy problem.